equations. So we have also introduced the propagation of electromagnetic waves in this media, and also some experiments and the pricing of the companies that we have chosen.
First, let us describe what is chirality. A well-known engineer named Lord Kelvin describes chirality with the following proverb. I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. We have also here put an image of a carbonate nanotube, which is used as an additive to various structures in electronic, optics, plastics, and other materials of nanotechnology field. And it is a form of chirality. Chirality, which is also known as handness, is a geometric characteristic which describes objects that cannot be superposed on their corresponding mirror images by any means of rotation or translation. It comes from the Greek word chiral, which means hand, and it is also the fundamental example of an object exhibiting the property of chirality. For example, both our hands, even though they seem like the perfect mirror images of each other, in fact, they don't coincide precisely with each other. Here we have given some example of chiral materials that are found in everyday life. The range of objects that manifest chirality varies from microscopic to macroscopic scale. Helix shape is the most common and fundamental chiral structure found in nature, and all other manifestations arise from this shape. And here we have given the pictures and the examples of chiral materials. For example, the Mobius strip, the scissors, the shoes, the spring, the seashell snail, and the corkscrews. They are all examples of chiral materials found in our everyday life.
Here I have introduced the mathematical point of view of chirality. Any shape is considered to be chiral if its symmetric group doesn't have any isometry related to orientation reversing. This is the symmetric group of an object. Here are presented all the transformations, and here we can also see some rotations and the transformations of the objects. In Euclidean geometry, we have started the Euclidean postulates since in high school. We started geometry, and isometry, if we recall from linear algebra, can be expressed using matrices and vectors. For example, if we have a point or a vector denoted v, then we can use an orthogonal matrix to multiply it or to rotate it, and also vector b in order to move in a distance or something, where A is the orthogonal matrix. Orthogonal matrix is a square matrix. Rows and columns are mutually perpendicular but different from orthonormal. Here the rows and columns should have a unit length. The determinant of matrix A can also give information whether the isometry preserves orientation. If it is 1, it preserves, or if it is -1, it reverses it. The manifestation of chirality in three-dimensional, the shapes that don't have the mirror plane symmetry, the center of symmetry, or higher earth reflections are considered to be chiral. But this is not always the case, since there are examples that lack the aforementioned properties and are still achiral. Here I have plotted some points. Here are some points that constitute this figure here. If you see in the 3D, in this picture that I put here, these points seem to not have any relation with each other or any sort of symmetry. But if we look it in a planar view, we can neglect the colors, because the colors introduce chirality. We can see that this figure has a sort of symmetry, and this is the coordinates here in this rotation here are invariant; they do not change. In 2D, it is easier for shapes to be achiral because the line of symmetry is enough. If an object has a line of symmetry, then it is considered to be achiral. It is needed to measure the amount of chirality in different dimensions. For this reason, the chiral index that we will describe also later should handle the special cases of Euclidean spaces as below. For example, if the same points have identical coordinates, then we have learned that in Euclidean postulates and Euclidean geometry, a point is considered to be weightless. But if same points have identical coordinates, then we have to introduce also the weight of a point. Also, we have to consider continuous and solid shapes, and chirality is also dimension sensitive. For example, an isosceles triangle is achiral in 2D, but when we jump to 3 dimension, it is chiral.
We gave examples of chirality in our everyday life, and now we have studied chirality in chemistry. Most of organic molecules studied by scientists have the chemical M-helix model, as in our everyday life examples. The enantiomers of the same molecules may show the same chemical and physical properties, but they will react with different molecules. The difference in their properties may be crucial. For example, one enantiomer of, for example, here we have the importance of differences in enantiomers and the different properties they possess when they react with different materials. The first example is ethambutol, and the right-hand enantiomer of this chemical is used in medicine to treat the disease of tuberculosis. Meanwhile, the left-hand enantiomer can cause optical neuritis, which leads to blindness. Also, another example we have mentioned is dopamine. And one form of dopamine is effective in the management of Parkinson's disease and its treatment. Meanwhile, another form of dopamine can cause the reduction in white blood cells. This shows the importance of chirality. How to distinguish between enantiomers. In order to differentiate between different enantiomers of the same molecule, the response to a particular polarized light, which is related to the optical activity phenomena, is monitored. Even though this interaction with the polarized light of the chiral molecule is low, much larger effects can be observed in artificial chiral structures.
When I was reading some articles about chiral molecules, I came across of research of Harvard. They were stating these different properties, and one interesting fact was that the sugars were left-hand enantiomers. So if we were to eat the mirror images of these sugars, then our body could not metabolize them, and then we would starve. And this is utilized in some artificial sweeteners such as tagatose or naturulose that are the mirror image of the milk or sugar, and they taste sweet, but we cannot absorb by our organism, and then they have 0 calories. Now it is being researched, this topic, because they want to use this property in order to control the glucose level in our blood and help the people who suffer with diabetes or things like that.
And I like this slide. The first one.
Thank you. About the chiral media, we expressed the chirality in general, but chiral media now is composed of particles that are chiral. A chiral medium, just like the hands with the gloves, where the right hand fits only the right glove, here the chiral media respond to waves that are left-hand or right-hand circularly polarized in different ways. Also, these electric and magnetic field vectors that pass through this medium are cross-coupled, as we can see. And here we can see this arrow sliding and determine the clockwise direction of rotation. Chirality, as mentioned earlier, is nothing but a geometrical property, and it doesn't need to originate from molecular level. It can also be constructed by inserting chiral structures in a hosting medium that is not chiral. 2 scientists that I've mentioned here are actually 2 Italian chemists, Credi and Baroncini. They found a way to combine molecular chirality, the natural property, and the motion of these molecules in order to create a molecule that can switch from chiral to achiral and vice versa. as we can see here, they bind this rotor part in the molecule, and here we can see the rotor part and also the molecule, and here is the mirror image, and when it rotates here, just like this in the figure here with the blocks, it can go back to its original shape.
We have also analyzed the optical activity and the chirality in atomic and molecular level. The circular birefringence, which is one characteristic of the chirality. Chiral molecules are characterized by the ability to rotate the plane of polarization of the light that is passed through them. Enantiomer cause rotation in equal magnitude, but in opposite direction. And according to the direction they rotate, they have two names, which are dextrarotatory, which is the rotation to the right or clockwise, and levoratory, which is the rotation to the left or counterclockwise. This optical rotation is known as circular birefringence. In different chiral media, electromagnetic waves that are circularly polarized and of opposite chirality propagate with various velocities, and as a result, when propagating through a Hennes medium or a chiral medium, polarized waves collect different amounts of phases. One important parameter here is the refractive index, which we have also mentioned in electromagnetic waves, but here differently, it is a complex number, and it is found by the formula that we have written down here. Also, the chirality is described using the difference between the light and the left and the right refractive indexes, and it is found by subtracting the right index from the left index.
Here we have this,
yeah, prețată mare să folui.
No, I can listen to you, but I had a emergency phone call.
Also, it exists an instrument that can measure the refractive index, which is known as the interferometer, and it is composed of the light source, which is here. Here we have two pictures. The one is the real life picture, and the other one is a planar picture. We have the light source, we have two mirrors, and also photo detector, which measures the index, the refractive index.
Circular dichroism is another phenomenon that accompanies the circular birefringence, and it is the differential absorption inside the chiral media of the left hand and right hand circularly polarized plane waves. In order to determine the enantiomers of a chiral molecule in a given substance, we use the spectroscopy of circular dichroism. There is a table that chemists have constructed, and they would show also the rotation and the degree of chirality of molecules. Circular dichroism is mentioned in this way. If the intensity of the light is I0 and it is expressed as the average of left-hand and right-hand polarized wave intensities, then the circular dichroism is expressed with this ratio. Different from the circular birefringence that Eminem mentioned, this one is proportional to the imaginary component of the refraction index difference. This is the short video here. We have a propagation of electromagnetic wave in the chiral media, and here at the output, we can see the rotation here that is counterclockwise, or we can say that it is like a left-hand rotation. Propagation of electromagnetic waves in chiral media. In order to use the Maxwell equations, we have to make some modifications, because even in the textbooks that we study, it is left unmentioned because it introduces a lot of complexities in the calculation. We have to introduce this dimensionless parameter, chirality, and it is introduced to describe the handedness of different substances, and in this case the permeability conductivity and permittivity are complex and depend on the frequency. These are the well-known relations that we know for the fluxes, electric field, electric flux and magnetic flux. And using the Telegram form, I actually found these equations in the book that you suggested, the Orphanides book. This is it's known as Telegram form, and we can express them like this, and these are actually the relations for biisotropic materials, or differently known as chiral materials. These equations seem okay. So we have here the Maxwell equations. We have studied before, but now we have to replace the magnetic field with the newly obtained one, and these are the equations of electric and magnetic field that satisfy these relations here, and this n here is used for the 1 and 2, which I denoted with clockwise rotation and counterclockwise rotation. And to cut it short, this is the relative chirality that is actually used, and that's why it is used in this form here. These are the phasor notations of the right hand and the left hand rotate polarized, and here we have the propagation constant.
We have also mentioned some of the most important experiments conducted in chiral media.
Mm-hmm. Actually, can I ask one thing, Bjorna? For some reason, I was when I muted my microphone, I cannot bring back your presentation. Is it possible for you to turn off the sharing and start sharing it again? Sometimes this is the only way for me to get it back.
Okay.
Profesor, și mă să përpindoni ekrane kështu.
Jo, po bëj pin prezantimin e Bjornës disa herë, po prapë s'e shoh dot. E provova. I was seeing it. I can see it back. Now, e shikoj. Shumë mirë. Okay, now the presentation was good, but one thing that I want to ask you is the following. So we discussed about the length scales, or what we generally care about the length scales is something that we have to do it ourselves, okay? Which is something which can go down as 0.5 micrometer. This is how small we can make these. But now what about the chiral media? What is the length scale where you are operating?
Okay, so I made some, when I was reading some research papers of other scientists, I came across a frequency range that was used, it was from 1 gigahertz to 1000 gigahertz. And this is the frequency where the maximum absorption occurred in this chiral media, and the wave is not reflected back, it is totally absorbed by the chiral media. But chiral media are also used in coatings of, instead of dielectric coatings, we can use chiral coatings, and they have dimensions from 5 centimeters to 10 centimeters.
Okay, but can I make a comment here, Bjorna? You said that I asked about length scales, which are measured in meters. You mentioned the range in the frequency domain, which is good because they are inversely related with respect to each other. So you have the gigahertz, you take the speed of light divided by the frequency range, which you mentioned, you get the length scale. But now, since you are dealing with molecules that are chiral in their natural forms, which is all optical chemistry, which is one part of chemistry, which is the most difficult part of chemistry, which I found it very difficult. But these molecules, they are very small, which means that miraculously, you have now a medium, which is molecules, we don't have to construct it, it's relatively small, which means that it's a length scale range, which we are lucky to have it in a natural form. We're lucky that we don't need to make a nano angstrom length scale of a molecule, right?
Yes, yes. In the products that constitute the chiral media, we have the cholesterol liquid crystals. They are used because they can switch to chiral and achiral in a very low temperature. Yes, we have mentioned them.
We have mentioned them in the other slides.
Okay, that's good. But now I just wanted to...
We can see the molecules, and they are very visible. They are in the powder form in their solid state when they are sold, but in the experiments they transfer to liquid state.
Okay, you can see the molecules in their powder form. just the powder, okay?
We can see the matter that constitutes of these molecules only, because the molecules can be viewed only with very powerful microscopes.
Okay, that's good. Okay, then someone has any question? This was really a very good topic to discuss. It was also nice explained.
We
We
have
talked also about the rotational matrices, which is the orthogonal matrix, or you can call it also orthonormal.
We have also some
we have
short,
also other slides.
Oh, you have
some
more?
short
Okay.
slides
Yes.
too. Yeah.
Just move faster then, because you took
Okay.
good bunch of
Okay.
time.
Oh, we have measured some of the experiments conducted in chiral media, and they are mostly done with two antennas, one receiving antenna and one transmitting antenna, a sample holder and a sample. But this kind of experiment had a problem because the antennas were too close to the light, and it may presented some error, and that's why the scientists also added a concave ellipsoidal concave mirror. Also, each part of the antennas are connected to a network analyzer that measures the phase and the magnitude, which determine the chirality.
Okay. This is the waveguide method to describe chirality, and the most common setups use the circular waveguides, because in rectangular ones we cannot observe the rotary dispersion effect. Here we have the chiral sample, and this is the real life experiment, and this is only the sample, and here we have the place where the beam of light enters and where the beam of light leaves, and they also make the transition from rectangular to circular, and this place here is used to rotate this one in order to obtain the rotary effect and determine the chirality of the molecules. These are the companies that we have chosen to cut it short, and these are the...
Okay.
We have analyzed two companies and compared their prices for the same amount of material.
Yes, we have 25 grams, 100
Yes.
grams. Here are the liquid crystals that are sold in the powder state. I have mentioned some of them. This one here, for example, cholesterol acetate, is present also in our body and is normal human cholesterol ester. But this one here that is sold in a closed container is very dangerous. It is cholesterol chloroformate. It's very hazardous, and if it's not used with proper safety measures, it can cause severe skin burn and eye damage. One interesting liquid crystal is the last one, the cholesterol oleic carbonate. This one is, I don't know, maybe you have seen the opal. It's a precious stone. This one causes reflections of light that are similar to this precious stone, and this also can be used as its substitute when we construct the fake jewel. I don't know if you have seen the opal stone before.
No, I haven't.
It's very similar. I will show. This was the presentation, by the way. Thank you for the stone. I can show you the opal.
Thank you very much for your presentation. And
this is the opal stone. I don't know if you can see.
Opal stone. We can see it right now. Yes.
Yes, but this please... one and that oleic carbonate makes similar reflections of the light.
But the take-home message is, I want you to really always care about the length scales. So the technical language you should always communicate with each other is, what is your length scale? What is your time scale? What are you measuring? Microseconds? Are you measuring in terms of length scale, microseconds or millimeters? Sorry, micrometers, etc. So these are essential concepts which you should always look for. Okay. Thank you very much again for your presentation. We can continue with Ionel.
Përshëndetje, profesor.
Përshëndetje, mund vazhdoni?
Po, patjetër.
You start sharing the...
Për shqetësim, po e kishim me detyrim e bëj sot, profesor.
No, it's fine. It's fine. You can continue. Okay.
Profesor, mund ta shihni prezantimin?
E shikojmë, po.
Okay, atë po vazhdoj.
Yes.
Okay. So our topic was nonlinear optics. So more specifically, what is the application aspect of nonlinear optics? So What is nonlinear optics, first of all? Nonlinear optics is the science that studies the behavior of light in a nonlinear medium, which the most common used are nonlinear crystals. This means that the polarization of light, P, has a nonlinear response to its electric field, E. So both the pictures display a polarization process. Each, in the first picture, it is shown a linear process, which is like having light pass through a linear material like a window glass. Then in the second half of the picture, we have a process called second harmonic generation, or SHG, also known as frequency doubling. It is a process where two photons with the same frequency interact with a nonlinear material and generate a new photon with twice the energy and the frequency. So
Yes.
we can see is this right here. We can also see another nonlinear polarization process called some frequency generation, or SFG, based on the annihilation of two input photons at angular frequencies, omega-1 and omega-2. In this picture, it is like omega IR and omega VIS, while simultaneously one photon at frequency omega-3, or as this is displayed, omega SFG, is equal to the sum of two first frequencies generated. The other pictures the other picture displays two other processes called third harmonic generation, or THG, and four-wave mixing, or FWM, which are third-order effects with different NL indexes, or in other words, reflective indexes. We are going to talk about them later.
Okay, Professor, in this slide, we have some hand-drawn sketches. We can see some different sort of non-linear processes. The sphere represents photons of different energy and frequency, and these curved lines represent a non-linear material, for instance, BBO crystal. We see in the first sketch, that is Lionel there, that a photon which permits through a non-linear material and generates two photons of different energy and frequency. However, we should know that photons are elementary particles and you can actually split them. But BBO crystals absorb them and use a vacuum energy fluctuation and create two other photons. The second sketch displays basically some frequency generation CFG process where the opposite happens. Two photons permit through a non-linear material and a single photon of higher energy and frequency. The last sketch represents a photon permitting through a series of materials, and the outcome is a photon with a frequency not omega. This that I just explained are implied by the formula here that is below, where chi1, chi are variables is a tensor. Chi variable is a tensor that represents which non-linear order we are going to execute. Represent linear optics. Chi2 represents second order effects. In other words, nonlinear optics displayed by first and second sketch. K3 order effect, and so on. If we take a look closely, our last sketch is a representation of a polarization density, K5 variable. We start by K2, which is displayed by one of these curved lines, and then continue K3, 4, and 5. And go to the slide 4, Manuel.
Okay, so before I go to the next slide, this one is called a DFG process, which states for difference frequency generation. This first one here.
Sorry, Yoneli, I'm slide 4. Is it? Are you showing? You are still on the same slide, right? You didn't change.
Yeah, I'm still in the same slide.
Okay.
I'm just making clear something about the first sketch. This one is another nonlinear process called DFG. This one is SHG, which we talked about, and this one is the five order polarization process.
Yes.
As we see, the polarization formula is dependent on the chi variables and the electric field. So it makes it dependent to wavelength inevitably, and it is not shown in this equation, but P, which is but P is a time domain variable, let's say. So what are some materials used in nonlinear optics? The most common used tools or materials in nonlinear optics are nonlinear crystals. They are non-organic materials which make possible that at least one of the frequency mixing processes, which are SHG or second harmonic generation, DFG, which states difference frequency generation, OPA, which is optical parametric amplification, OPO, or optical parametric oscillation, OPG, or optical parametric generation, CPDC, SPDC, sorry, which is short for spontaneous parametric down conversion, and OR, which is optical reflection. We are not going to dive too deep in each one of them. However, we are going to show you a cool demonstration of one of them later on. And this here is the structure of KTP crystal, which is one of the non-organic materials used for polarization or non-linear light process.
So here we are going to talk specifically for these two crystals, LBO lithium triborate and the BBO beta barium borate that is in the picture. They are the most commonly used ones. We can show the structure of each crystal in the first picture. No, and both of these other pictures show graphs of wavelength in the x-axis and the reflection percent in the y-axis. The way that the graph fluctuates displays also how these two crystals are different and how does the light behave in each one. The first graph is more all over the place, and the other graph looks more stable.
Okay, so the difference between them. BBO crystals are high have high transmission at the deep UV band, have wide phase matching range, and have high conversion efficiency. This is a picture that shows what a non-processed BBO crystal looks like. And it is we have to say that the BBO crystal is the most used nonlinear crystal.
What frequency generation does the BBO do?
We are going to show them in another slide.
Perfect. Very good.
Yeah. This one is LBO crystal. This is how it looks, unprocessed, and it has a higher damage threshold, and it has better inner crystal quality. This crystal is the best for SHG process or second harmonic generation process for high power system of 1064 nanometers, which is an infrared wave. Which is the wavelength of an infrared wave.
Yes.
So we have the prices. At the prices, we do not show only the price in dollar, but also the characteristics of each one of the crystal. So this is what I meant, that we are going to show the wavelength that these crystals process.
Okay.
So at the characteristics, this one, for example, the first BBO crystal is a nonlinear crystal where the first 3 digits display display the dimension size. So it's 6 by 6 by 1 millimeter, and so and the last digit represents the wavelength of the lasers or the waves that these crystals are able to take through a polarization process. And then we see the prices. So we can see that the first one costs more than $500, and so on. As we see, these crystals are not cheap. The first ones are from a company called Edmund Optics, and the second ones are from a company called Ferrolabs.
Okay.
Yeah, this is this shows the specifications of one how's it called, wheel, pinhole wheel with a BBO
Pinhole.
crystal.
You can call it pinhole.
Yeah, pinhole.
Oh, it's a pinhole with a BBO crystal inside?
Yeah, it's a BBO crystal inside, and this is a pinhole disc.
Oh, okay,
Pinhole
that's strange.
wheel.
Never thought about this one. It's an interesting design.
Yeah, it has a 6 millimeter dimension here, and we can see the coating applied. The coating applied for this one is anti-reflective coating, which can coat waves from 400 to 800 nanometers with a reflective percentage of an average of 3%.
So you don't lose light. All the light is transmitted on the other side.
Yes.
That's
yes.
Good.
Exactly.
And what is the size of the pinhole?
The size of a pinhole is this one. I think is
diameter. It's inch. It should be inch. Is it 5.7? What is it?
No,
Can you zoom in?
This one is I think this one is a 16 stop. Is a 16 stop, and it ranges from I think 1 micrometer. Can I check in?
Yes, you can.
Yeah, just a second, please.
You can go to the next slide. Actually, it's fine.
Okay.
Go to the next slide. We can discuss that later.
So there are solid ones with a half-inch to 1 inch diameter, and there are 16 stop ones with a range from 5 micrometers to 25 micrometers.
Okay.
So why do we need them? They can be used to create UV lasers. They can be used to change the laser color, and they can entangle photons. I forgot to put the caps here.
Entangle? Why? No, it's good. It's hard to make it, but they claim so.
You cannot actually entangle photons because photons are as Nico said it, photons are how's it called?
There are bosons, but I don't think you want to say that there are bosons. Photons, there are a lot of things, but they have small scattering cross-section. They don't interact as good as electrons can.
Yeah, they are elementary particles, so you cannot actually entangle them. Yeah.
Okay.
That's the word I was searching for.
Why do you claim that they entangle photons? So somebody's
we claim that they entangle them because these crystals entangle them because they actually absorb them, and through vacuum energy fluctuations, they create one or two other photons
Oh, okay.
to
Well,
different wavelength and energy.
that's actually the the particle physics analysis of the creation of the photons in a nonlinear crystal. I don't know if this has ever been made. If it has appeared in the literature, I would most probably personally I have not heard about of it. Okay, because that's a terminology which is used in particle physics, and it's a beautiful part to discuss about. But probably, yeah, in the nonlinear optics, if you take a course on PhD level in nonlinear optics or in electronics engineering, we don't generally talk about particle creation from the vacuum fluctuation. This is too much to grasp.
Yeah, you're right.
But that's fine. We can go ahead.
Yeah, let's go ahead. So, what are the industries that we can use? That we can use this. So it could be army.
Okay.
It could be the process of creating UV light, which is used for various things.
Mm-hmm.
Yeah. So this is from Therolabs. We found some pinhole wheels. Yeah, this one is the one I talked about. The precision pinhole mounted in half an inch or 1 inch disc. So this disc is half an inch or one.
Mm-hmm.
Ingle pinhole sizes from 1 micrometer to 1 millimeter. And a 16 position pinhole wheel with hole sizes from 25 micrometer to 2 millimeter.
Okay. Now this Therolabs most probably is called Thordabs. You might double check the spelling because it's a huge disrespect to a wonderful company. Really, I mean, so it's THOR Labs. But double check that one and it's fine. Just as
Of course.
Unless some other company they really wanted to steal from their good name and call it Therolabs.
It is Thorlabs and it is displayed here.
Good. Okay.
Sorry.
Let's move ahead.
Here, Thorlabs.
Mm-hmm.
So before the end, Nico and I were wondering what else can we do to have a better presentation for this topic, and we could not find any videos online of 3D animation or something like that. So I created my own.
That's perfect. Let's see.
Yeah, this is the 3D compositions that I use in After Effects, and this is the rendered video. It's only 19 seconds, and I will guide you through it. So this one, sorry. So this one is a crystal, is the BBO crystal, for instance. And this red cylinder right here represents a laser.
It is red, right?
Yeah, it is red.
It's red, so it's 600 nanometer. I'm writing it in the comment section. Yes.
Yeah, it is 700 to 600 nanometers. So it goes through the crystal.
Non-linear crystal, yeah.
Non-linear crystal, and as we see, the wavelength and the frequency change. The wavelength, hence the frequency changes, and since the frequency changes and becomes larger, and the wavelength becomes smaller, we have a transformation of this light. So of this light's color.
What is the wavelength coming out?
The wavelength is something around 300, 350.
Yes, okay, that's good. This is second harmonic generator.
Yeah, this is second harmonic generator. So this is the output light, this is the input light, and the frequency changed, hence the wavelength, hence the color change.
Okay.
So this is the most I could do with After Effects.
No, this is good. This is really good. So actually, you said that you have an incoming 600 nanometer light. I'm trying to make the relationship now. So if it is 200 nanometers, that is inverse with the energy. Energy is 6 electron volts. Now you have 600 nanometer, which is 3 times larger. The energy is 2 electron volts. Okay. Then outcoming is 300 nanometer. I'm going to write this in comment section. So this is going to be half. The energy is 4 electron volts. Good. So regarding the scale of the energy, I wrote a comment before. If you see in the comment section, it's 200 nanometer photon is 6 electron volt. Now you are saying that you have a 600 incoming. So 600 nanometers. This is equal to. So the wavelength is 3 times larger. That means that the energy is 3 times smaller. So this is 2 electron volts, I believe. Yeah, 2 eV, 2 electron volts. Then this means that the output is 300 nanometers, which is equal to. Wait a second. So the 600 you divide it by 2, so the energy is twice as big. So it's 4 electron volts.
4 electron volts. Yeah.
Okay, so that's good. So you said it right. So these are the BBO crystals and the KDP or KTP LTO. This is really a very beautiful part of optics, because this has to the beauty of all of these high energy lasers, which can be excited into high frequencies. This is really represented from the equations you explained in third slide, I believe, where you had the.
Yes.
This was a very essential slide, but that is made possible only for very high power lasers. Okay,
Of course,
happens most of the time. This happens
if
in pulse lasers. Sometimes it cannot even operate at continuous lasers because the power is low. But now the pulse lasers, they have the pulse in a pulse lasers. So let me write it in the comment section. Lasers is 10 nanoseconds. 10 nanoseconds. So 10 nanoseconds, that's the time scale. Okay. Now you have a constant energy. The power is equal to some energy divided by the time. So this means that the power, which is equal to energy divided by nanoseconds, which is 10 to the power minus 9. That means that this is equivalent to multiplying by 10 to the power 9. So this is a very huge power. So
huge power.
Do this, and these crystals. What has happened with these is that the prices have been fluctuating a lot, because initially these crystals, they were very hard to grow. These are grown crystals, so they melt the material and they try to construct them. It's good that you have read a lot about those, but for a long time the price was so high that people in research, they would use unreasonably small crystals by focusing a very large laser beam into a very small volume, because they did not have the BBO crystals big enough. But then after 5 or 10 years, Chinese companies, the Far East Asian companies, they started to produce much larger BBO and KDP crystals. So black market was flourishing from China to US. I'm saying black market because you could not buy those at those times. But those things which are as big as 5 millimeter by 5 by 5, which is something you can hide it in your pocket, this could sneak through the customs in a very not correct way. But anyway, researchers were able to do research sometimes this way. But then the prices dropped because technology was improving better and better. And now you can really see that with the size increase of these crystals, the price also jumps quite a little bit. But anyway. Okay, so BBO that you were discussing, actually, that can have an input wavelength of 600 nanometers and can output a wavelength of 200 nanometers once it is operating in the third order, how do you call it? Third order frequency generation.
Fluctuation.
And then that means that 200 nanometers will be 6 electron volts. 6 electron volts, if you have 3 photons at 6 electron volts or at 200 nanometers, which you cannot see, it is blue color, it's ultraviolet, you can ionize an hydrogen atom. That is the part or the point where you start ionizing components in the region where you are working. Okay, who remembers the ionization energy of the electron? Of hydrogen.
The what?
The ionization energy of the hydrogen.
No, I couldn't remember that.
There is this 13.6, you might remember from chemistry. 13.6 is the energy required to extract 1 electron from hydrogen atom. Okay, this is a benchmark value. Some of you might have memorized this one from chemistry. And 3 photons of 200 nanometers, they can ionize a hydrogen atom. Okay. Anyway, so it's a three photon process.
But we have to say that BBO crystals do not capture every photon possible from the light, from the laser.
What do you mean?
So when the light of the laser passes through or permeate through a BBO crystal, the BBO crystal actually catches 1 of 100, for instance. I can.
Oh, you mean conversion efficiency?
Yeah, conversion efficiency. It
Okay,
doesn't.
okay, yeah.
It
So
doesn't convert it doesn't have 100% conversion efficiency.
That is correct. Okay, that's true. So if you see the histogram of the photons that go in and leave the let's say the BBO crystal, the incoming frequency, it might be traditionally something like this. So you have the frequency of this is 200, this is 400, and this is 600, and the incoming, it's all into the 600, and the outgoing. So you said 1% is used. I don't remember the exact values.
I don't remember the actual percentage, but it is it's a really low percentage.
So I hope you can see this drawing I tried to put together. So you can see from here in blue, I showed the incoming wavelength of the laser, which is at 600 nanometers. This is the incoming blue. Then the outcoming, you said that the conversion frequency is low. So in the output, you wish you had no 600 at all. Why do you need it? You want to convert it all, but no, that's true. Some percentage, this is the histograms. The area of this curve, this shows that quite a lot of photons are not converted at all. Then you have in red, this is the outgoing, right? 400 nanometers, you have a second order generators. I don't know what is the second order generation efficiency for this specific wavelength, but still you have the 400. Then you have also a little bit of 200. Now this 200 is a little less, of course, but this is how the graphs can look like. So the area in this histogram in blue, which is the incoming lasers, should be equal to the area of the histograms of these photons in red at 600. These photons drawn in red, outgoing beam at 400, plus these this small number of photons at 200 nanometers. And so the conversion efficiency is an issue, but then since the number of photons which are outgoing at 200 nanometers is a small value, that means a low intensity, and this means that researchers have to pump up a lot the power at the incoming laser beams because there is nothing else that they can do. Okay, so that's why they might need to use pulse lasers that they've used for a long time, and they might manipulate the light this way, and then they can use it in their experiments. This was really a good presentation. I like the three-dimensional drawing or the simulation where the beam is going in.
Thank you.
What could be really amazing would be this actually, but I'm not asking you to do it right away. So you might have like a nonlinear crystal going this way, and then you might have an incoming wave like this, and then the outgoing beam. This would be actually, if you can make this, would be amazing. So let's try to see what I'm trying to put together here. So you might have a beam which is incoming in blue, going into the crystal. The outgoing beam is 600 here, 400, 200. So all of those, unfortunately, are there, generated after as an output of. And the 200, you can show it in dark blue because it's ultraviolet. The 400 is blue. The 600 is in red. In terms of the optical wavelength or the optical visible range that we can see, those are the respective colors of the rainbow. You can do it?
I think so.
Okay, that's good. then you do it, Anil. Okay, any question for Nico and Lionel? Okay, so now I think regarding the nonlinear crystals, we cannot make much comments regarding the length scales, so we can leave it for now. But always, I'm trying to find the relevance of length scales, time scales. This is how you should come up with beautiful questions whenever you see any presentation. I can stop this section, this recording, and